very good morning to all of you. My name is Saravanan Balasamy. So today I am going to share the experimental work that we have carried out in IIT Hyderabad. So the title of my talk is Swirl-Stabilized, Turbulent, Premixed and Stratified LPG air flames. So it is like a model combustor for a gas turbine, land-based gas turbine. So you can see an example of how the flame will look like in this kind of combustor. So first, why do we need to choose the LPG? LPG is gaining the market. One strategy says global LPG market is expected to reach around $360 billion. So we are slowly moving from coal-based thing to LPG-based thing because it offers a lot of benefits here. So you already knew that we are using in a domestic application. It has reduced a lot of indoor pollution, and it is used as a fuel for auto transport sector, both in cars and as well as in mega ships. And you have land-based gas turbines also. LPG as a fuel offers a lot of benefits. One important thing is the clean burning it has. So it produces no soot, it produces low amount of NOx and almost zero amount of SOx because there is no sulfur in it. And it is an environmentally friendly fuel, and it has a similar combustion characteristics like a DME. Okay, in fact, we started with the DME, but we couldn't procure it. It was very expensive, so we switched back to LPG. So it's just a snippet of what are the previous studies happened on LPG. Okay, so people have studied in both fundamental level as well as in application-oriented levels. Fundamental level, in that sense, people have looked into the pressure, laminar flame speed, all those things. So you try to understand what is happening there using closed vessel or spherical bomb, and also about application point of view, like how that as a fuel in a SI engine, a spark ignition engine, how it can be used in a heavy duty LP/LI engine, and also the swirl-stabilized burners for land-based micro GT kind of combustion chambers. So if you see in this list, most of them are focused on the premixed. What is premixed means that fuel and oxidizer are brought into molecular level before they enter into the combustor. But in most of the practical applications, you will also start to go into this non-premixed or partially premixed one, where the fuel and air is not fully premixed. It still has to mix thoroughly before it enters to the combustion chamber. So that is the one interesting area which allows us to improve the efficiency and reduce the emissions. So that is the one thing we are going to see now. So I'll just show you two examples. This is the work from Coast, Saudi Arabia. So what they are doing is they are working on combustion characteristics of Swirl burner. So the primary idea is you have a central mixture, then you have two annular sections. So they provide annular mixture and outer mixture. So basically they create a radial stratification. Okay. So as we move radially, you will see a different equivalence ratios. And they allow that flame under different conditions. Like one example is that you play around with the velocity ratios between annular and outer mixture. Okay, let's say the range is given here, which is called MR, which is nothing but annular mixture velocity by outer mixture velocity. In the first case it's 2.2, in the second case it's 4.9. All other conditions are kept constant, and you can see how the flame behavior has changed. It is very close to the burner exit, whereas here it is pushed further down in the downstream. Why? Because the reason is there is a higher annular momentum which is increasing that, and it changes the flame shape and pushes towards downstream. So the problem where this one is, it may lead to the blow off. Okay, a flame instability happens. So we don't want to enter into this, but it's just one example how we can use an operating parameter to move from unstable flame to stable flame, vice versa. Then there is another interesting thing in this turbulent, premixed and stratified combustion area, which is the Cambridge Sandia turbulent stratified flame. This combustor is very well known in this combustion domain. So where you have a bluff body in the middle and you have two annular sections. One is called inner, the other one is called outer jet, and after that it is surrounded by a co-flow air. So the idea here is we can create two different equivalence ratios, and we will see how that flame interacts with that. Here is one example comes from that burner. So what you can see in the right side is the mixture fraction or equivalence ratio. This is the inlet, and the red shows that both the inlets are having the same equivalence ratios. So that is called premixed combustion. So the corresponding velocity field is shown here as a streamlines. So you can see there is a nice recirculation zone on above the bluff body, and this flow velocity is also different. You can see the green in the inner and reddish in the outer. So that shows the velocity gradients are there. So the velocity in the inner is lower than the velocity in the outer jet. So they can see the velocity gradient, how the flame interacts with the velocity gradient. The other thing is, they also studied about how that is interacting with mixture stratification. So you see here red and green. So what that means is, red is very close to the stoichiometric condition, whereas lean means you have more air than the fuel, a lean mixture. So here the phi gradient or equivalence ratio gradient is like this, whereas here the equivalence ratio gradient is different. And you can see the impact on the velocity field also, okay? So this is plays a very important role, like when the flame encounters a partially premixed gradient, how the flame behaves, whether it is stable or unstable, how that is behaving with the different strain rate. That is a key question here. I'd like to touch upon a little bit about the fundamental here. So why that mixture stratification effect is important and how it is complicated. Let's say we are sitting on a flame front and we are near this stoichiometric equivalence ratio. That means you have right amount of oxidizer to convert the fuel into products. Now suddenly the flame is encountering a mixture pocket which has a lower equivalence ratio. That means it has more air than the fuel required. So then if the flame moves from equivalence ratio 1 to this lean mixture, then what happens is there is something called memory effect. The adiabatic flame temperature for equivalence ratio 1 is higher than the corresponding adiabatic flame temperature for lean mixtures. So that means you are going to provide extra heat and radicals from this already burned zone to an unburned zone, okay? So this is called back supported flame. So the idea is this excess heat flux and radicals will support you to propagate faster into a lean mixture, which otherwise would be difficult to do it in an homogeneous lean mixture. So what happens when we have a situation where the flame moves from a lean mixture to a stoichiometric mixture? So now the situation is opposite. The mixture has more support in the front side because it will have more radicals and heat. So this is called front supported flame. So far we have a clear understanding if flame moves from stoichiometric to lean mixtures. But what happens if it is the other way around? Suppose we have a pocket where there is a rich mixture which has more fuel than that required. So then it get a little bit complicated. So we may have a situation where we will have extra heat from the recirculation zone, which will allow us to support the flame to propagate faster into a rich mixture. Or also, if you are moving the other way around, if you are moving from rich mixture pocket to lean mixture pocket, then we may have extra radicals like H2 and CO, which will allow us to support the flame and propagate faster into lean mixture. So these two are maybe back supported. We haven't fully understood yet, and that's one of the reasons what we have to do this one. So rich mixture, what is the relationship between heat flux and these chemical kinetics? How they interact each other, whether they balance, they support, or they become negative, okay? So that's a key question here. So we want to know what is the stability of LPG air flames at various premixed and stratified conditions for gas turbine applications, and how is that compared with the other traditional fuels, and what are the ways we can show that swirl flow conditions, how that is affecting the combustion behavior. So our objective is clear. We want to create a swirl-stabilized, premixed and turbulent stratified flame, and we want to see how that interacts with variable swirl numbers, and to see the stratification levels, how that impacts the combustion behavior. So with that in mind, we have designed this swirl-stabilized open type burner. It's a laboratory scale burner, which has a similar design philosophy like a Cambridge Sandia burner. So it also has a bluff body, inner and outer. Okay, so those three are common to the Cambridge Sandia burner. The one we differ here is that in that burner they used aerodynamic swirl. That means you have a tangential and axial entry. Okay, by modifying the mass flow rate between the two, we can create a swirl flow there. Whereas here we are using actual axial swirlers. So it's a solid body thing. So we have an independent way of controlling swirl flow as well as stratification. So we have more degree of freedom in this. So we have inner swirl and outer swirl, and if you do the cross section, that would help us to understand better. So you have a bluff body in the middle, and you have an inner axial swirler in the inner annular region. Then you have an outer axial swirler. So these are all 3D printed, laser 3D printed. You can see this is the inner swirler and that's outer swirler. And we have a co-flow laminar air to reduce the disturbance from the surrounding media. So the basic idea here is we will create different equivalence ratios. So we will have a radial stratification, and also we can play around with the different velocity. So we can play around with the recirculation zone size. So this is how the burner looks like, and that's a co-flow system. The green thing is again 3D printed to laminarize the co-flow air. This is the complete configuration of the burner, and this is the experimental facility we have with all the flow conditions here. So we have a flow, inner, outer, all the things are seeded with the particles. So we have a solid particle seeder as well as oil particle seeder. So we can do the particle image velocimetries to get the flow field measurements. And we also have a system tracers to add acetone kind of vapors to see the planar laser induced fluorescence. So basically you can measure the scalar field, like what is the mixture fraction, what are the OH and CH chemiluminescence, those kind of things. So this is our experimental setup we have there. So we have, you can see the PIV laser and PLIF laser here. We have two CCD cameras to do the stereo PIV, and we have the burner here sitting on a traverse, and these are all the PIV seeders. The configuration is quite enormous in size. So I'd like to focus on the test matrix. So first thing is we can do the inner outer swirler combinations. What do we mean? So we can change the swirler angle, okay, the kind of angle it creates. So basically we have these combinations. So inner and outer, they have either 30 degree or 45 degree angle. With that, it will create different swirl numbers. So the swirl number is nothing but what is a axial by tangential. So higher the swirl number, higher the tangential momentum you are importing to the fluid. So we have 0.47, 0.51 for 30 degree, and 45 degree we have 0.82 and 0.88. In the combustion community, people know that anything above 0.7 is like a medium kind of swirl range. This is, so we call that a low, and this we call as a medium. So we create 4 different combinations. So in the first configuration, inner swirl has 0.47, outer swirl has 0.51. In the second one we call LM. So we have put the outer swirl a higher number. So this is 30 degree, this is a 45 degree. And this is the other way around. So higher inner and lower outer. And finally both are higher in higher swirl angles. With that we can play around with the velocity of the recirculation zone, how the recirculation zone size changes. So the second combination we can do is play around with the velocity gradients. So either we have a momentum ratio of 2, that means the inner velocity is half of the outer velocity, or momentum ratio 3 where the outer velocity is 3 times of the inner velocity. So that will create more shear layer if we move from MR2 to MR3. So higher the shear layer, higher the interaction between turbulence and the chemical. The other configuration we have is we play around with stratification. Okay, so if we take 0.75, 0.75, that is premixed one. The equivalence ratio is same. The other combinations are, we say 2, 3, 4, 5. So basically we make inner richer and richer, outer leaner and leaner. Okay, so in the second case you have a stoichiometric mixture in the inner, you have a half of that lean mixture in the outer. In the third case, the inner becomes much more richer, 1.2, the other one is 0.4. So I'll show you one by one what are the flame behavior based on this test matrix. In all the cases, we kept total thermal input as 25 kilowatt. So the total amount of fuel we are burning in all the cases are same. Okay, to not to compare different configurations. So first thing is we applied a stereo particle image velocimetry. So the basic idea is you have a laser, you create a laser sheet. So you shine the test zone where you want to do the measurements. You add tracer particles, so they will give the me-scattering. And you have 2 cameras, 2 CCD cameras to acquire the image pairs at an angle. So they work like our human eye. Okay, so we create a stereo, so we can get the information in the depth also. So we call that as a 2D 3C. It's a 2-dimensional 3-component velocity. You have axial, radial, and tangential velocity field in this two-dimensional field we can gather. So we used both alumina and oil particles. Alumina particles we mostly use for reacting cases because we want to get information in the bond zone also. Oil particles we use it for isothermal conditions where the particle is anyway going to stay there. So this is one non-reacting or isothermal flow field, and the condition here is the outer velocity is twice the inner velocity. So basically the outer velocity is higher, the inner velocity is lower, like you can see here. So that is going to create a torque kind of thing. So basically you are going to create a recirculation zone above the bluff body. Why? The purpose here is that it will have a proper mix between bond and unbound mixture in a reacting case, so that it will allow us to stabilize the flame very close to the burner. So that is the idea here. So what we are seeing is an axial component, and the corresponding streamlines will look like this. So you can see that nice recirculation zone, the rotating stuff. So what happens when we increase the velocity ratio to 3? So now the outer velocity is thrice the inner velocity. So what you can see is now the recirculation zone becomes much more stronger. Actually, if you measure in terms of velocity component, this has more negative velocity. So that means the recirculation zone becomes much more stronger than the previous case. And you can also see the flame the flow field starts to bend because you are creating more swirl flow. So you are bringing it closer. Okay, so the streamlines start to bend more. So that's what we can see here. Now moving into the reacting cases. So we have done plenty of combinations. I'll show you a few of them. And the beauty of here is that it's all different combinations, but the overall fuel air mixture is same. That means 25 kilowatt, but we can generate this kind of flame or we can generate this kind of flame based on the conditions we have. To do the kind of qualitative information, we used chemiluminescence technique. So we have two ICCD cameras. Both of them occurred simultaneously, CH chemiluminescence and OH chemiluminescence data. So basically you put a filter in front of the camera. Based on the filter bandwidth, you can decide which one you are targeting. If you use 309 nanometer, then we are targeting OH chemiluminescence. If it is 431, then we are targeting CH chemiluminescence. So the corresponding image will look like this. So this is a time averaged information of 500 images. That is a OH and this is a CH. And one immediate thing you can see here is the OH seems much more broader than a CH. Why? Because CH chemiluminescence has a shorter lifetime than an OH chemiluminescence. So the OH will be dispersed more by the recirculation zone and burn gases. That's why this looks sharper than that one. Now the idea is if you want to compare different cases, it would be ideal to convert this volume or line of sight information into a planar field. So we applied a Abel inversion. So we can convert this into a flame sheet kind of thing. So if we exactly cut the flame in the middle, this is the kind of shape you will see. So this will allow us to see the changes in the flame structure based on different configurations. So this is OH and this is CH. As I told you before, OH is much more broader than a CH. Okay. And what happens now with the different effects? So first we will look into the effect of swirlers. So this is a configuration where we have both low kind of angles in inner and outer. So this is how the OH looks and the corresponding CH looks. And this is the condition where we have put a higher swirler angle in the inner stream. So you can start to see some differences. For example, the flame is trying to get closer to the burner, so the stability is actually increasing. But we can see more impact when we change the angle in the outer swirler. Okay, when we moved from 0.51 to 0.8, what we are doing is we are making more swirl effect. So more mixing happens. So the flame becomes like a V kind of shape because the recirculation zone has expanded and the flame is much more intense. Okay, so we can see more activity there in this configuration. Then this is a final one where we have higher angle in both the conditions. So you can see the flame becomes much more compact. So this is the flame shape and this is the corresponding flame shape if by simply switching the swirler angles from those things to higher things. Then there is another effect which is called the momentum ratio, basically the inner to outer velocity ratios. So if we convert from this to this, then you can see that at low configurations, we are not seeing much different activity. Even though that you can start to see some difference here, the flame is getting more stable, whereas we start to see more and more pronounced difference when we go to higher angles. So you can see the flame becomes much more compact here, and real difference is here. So the blue region is where, or black is the region where you have a high intensity chemiluminescence, and the red is the low intensity. So you can see that compared to this configuration, you have more chemical reaction happening, okay, higher the flame speed. So compact is the flame size, and this is the highest configuration. So higher momentum ratio and a higher swirler combinations. So you can see that the flame shape moved from this to this by increasing the momentum ratio and also increasing the swirler angles. Now let's look into this premixed versus stratified conditions. What happens when we change the equivalence ratios also? In this case, the equivalence ratio is same in both annular sections. So this is a premixed configuration. This is how the flame look like for a low swirler angles at MR2. And when we shift from this to this, now the inner equivalence ratio is raised from 0.75 to 1, and the outer equivalence ratio is moved from 0.75 to 0.5. And you can immediately see the flame becomes much more compact and much more closer to the burner. In a normal condition, it is not possible to ignite the mixture at 0.5 equivalence ratio. If it is a homogeneous mixture, there is no way we can ignite the mixture. But due to the stratification, we can still do this because there is a back support, okay, a back support from the flame which is here to the flame which is going to be there at 0.5. So what happens when we increase the stratification ratio? So here it's 1.2 by 5.4, that's the stratification level 3. So you can see that now the flame is start to move further downstream compared to this one, okay. So the activity is little bit going down because we will see more activity at 1 than in this configuration, and we can still sustain the flame at this extreme equivalence ratios. It is 1.4 here and 0.35 here. If you take an equivalent homogeneous things, we cannot ignite it, there will be a blow off, whereas here due to the stratification effect, we can ignite the mixture and we can stabilize it, and the flame shape is almost similar and much more compact than a equivalent homogeneous mixture. In all the cases, the total mass flow rate of fuel is same. Now what happens if we compare that with the laminar flame speed or adiabatic flame temperature? So you can see here at equivalence ratio 1.1, most of the hydrocarbon shows the maximum adiabatic flame temperature. And when we move to 1.4 or 0.5, you can see a very dramatic drop in the adiabatic flame temperature. But still, under stratification, we were able to burn it. Why? Because of the back support that I have explained. Okay, so this will allow us to make the flame more robust even under high strain rates. So if a burner has moved from a partially premixed to the stratified conditions, it can be less sensitive to the flame instability or combustion instabilities. So if you move further to MR3, you can see much more compact flame shapes. So what happened to the other configuration? So this is the highest swirl combinations, and you can see that flame is much more compact when we have both the combinations. So this shows that there is a benefit of moving from premixed to stratified conditions. How the velocity field looks like. So these are all the velocity fields gathered for reacting cases. So this is a axial velocity component and the corresponding streamlines there. So this is the configuration premixed one, and these are all the configurations for stratified cases. As you can see that when we move from premixed to stratified, the inner recirculation zone becomes much more stronger. So that is going to make the flame more stable and more robust to the strain rates. And when we go to the higher strain rates, we still don't see much difference in terms of streamlines. So the stratification actually helps us to become insensitive to the whatever mixture stratification happened, okay? So, and becomes more robust. And the same thing we can see when we have a MR3. Basically, the outer velocity is much higher than the inner velocity. Still, you can see the flame shapes are very similar compared to the premixed case. So, what I can show, or I hope I've convinced you, is that stratification of mixture increases both upper and lower flammability limits. So, it will make the flame more robust to the strain rates, and it will make the flame less pronounced to the combustion instability. So far we have done this, it's a preliminary work. Our next step is to do more quantification. So we are going to, we are under the process of procuring these things. So we can able to do the simultaneous PIV and OH-PLIF measurements, and we can also do OH-PLIF and CHO-PLIF. So that will tell us what are the local extinctions happening and how the flame is behaving. So I'd like to acknowledge my PhD student Dhanlakshmi Salan, Aj Murugan, and Professor Raja Banerjee, who bought all the laser diagnostics equipments. Pankaj Kohli and myself, we built the lab. Thank you.
Any question from the audience, please? Can you
emission characteristics?
Can you indicate?
Emissions, we started measuring it. Unfortunately, we don't have the cool probe. We are not seeing, the problem here is that we have a lot of co-flow air. That dilutes the emission comes out of the burner. So we may have to put a quartz tube to get a better idea.
Normally, the person comes across the question from the industrialist that will tell me what about the emissions.
Yes.
The emission is the key thing that is driving everything.
Yes. The point here is that as you go towards equivalence ratio of extremes, you know the NOx is produced mostly at 0.9 equivalence ratio. So we are moving away from that pre-NOx. So the NOx would be expected to be low.
And second thing, what about pressure penalties at the Swirler inlet?
Yeah, that's the point. We have to be with the low conditions. When we go to higher Swirler angles, we are going to put more pressure drops into the system, which may not be likable in a gas turbine industry. So even with the low, we can get a better stability here.
Any more question? Especially for the students. Remember, students, that there'll be a award given to the students, so don't miss out the opportunity. Now, in that case, let's thank the author again. Thank you very much.
Thank you.